Newton's third law states that for every applied force from an object A onto an object B, there's an equal and opposite force from B acting on object A. In terms of vector notation, if A pushes on B with a force FAB, and I should really have written a little arrow over this, Newton's third law says that B will push on A with a force FBA. Again, I should have written a little arrow here. And not by some accident, the force from B onto A is the negative vector of the force of A onto B. Now it's important to notice that this, in this case, is FBA. For a girl pushing on a wall, this is FAB. So the girl is pushing on the wall. This force vector is the girl acting on the wall. In other words, this is the force that the wall feels. This force vector is the force that the girl feels from the wall. And by Newton's third law, these are stated as being equal and opposite. But notice they're not acting on the same thing. The girl's force is on the wall. The wall's force is on the girl. Newton's third law just simply gives us a mathematical way of relating how these two things are related. And what's interesting then is it helps us explain, in a system with many bodies, how they interact with one another. So the girl isn't really pushing on herself, yet she manages to make herself go. How does she do it? Well, she pushes on the wall, and the wall in turn pushes on her. And as a result of having a push on her, she starts accelerating. In this regard, a lot of people get very confused when we think about very dissimilar objects interacting or exerting forces on one another. In a collision, for example, between something very massive like a train and something very small like a car, which is it that experiences a larger force? This is actually a real occurrence. This is a Burlington Northern train that collided with a car-moving truck on the tracks in Kent, Washington. And I think very often people get the mistaken notion that the train is exerting a greater force on the car than the car is on the train. But in reality, Newton's third law states that the force experienced by the car and the train are the same in magnitude, maybe the opposite in direction. But Newton's third law says that they're the same in magnitude. Now, why is it the car is all banged up and the train has just moved on down the tracks? Well, remember that the accelerations are not necessarily going to be the same. They may have the same force acting on them. By Newton's second law, acceleration felt by the car is the force exerted divided by the mass of the car. And since the mass of the car is very small compared to the mass of the train, the acceleration experienced by the car is going to be much bigger than the acceleration experienced by the train. And the train will just keep on going. Let's consider a situation where two people are mounted on roller skates and they push off against one another. We'll say that person A is right here, is pushing off on person B. So there's going to be force on person B given by FAB. Now, person B, by Newton's third law, is also pushing off on person A. So there's going to be a force exerted on person A from person B. Newton's third law tells us that the magnitudes of these two forces is the same, but let's suppose that this person B has a heavy backpack on, so that in fact she weighs twice as much as person A. In this case, after they've pushed off against one another, what will be the relationship between their two speeds? Will speed of person A be 4 times that of B, twice that of B, or will they be equal, or will the speed of person A be half of that of B, or a quarter of that of B? And how do we know? Well, the answer is that the speed of person A will be twice that of person B. And that's because each person's acceleration is going to equal the force that they experience divided by their mass. If person A weighs less or has a lower mass, then this number is smaller. If they're experiencing the same magnitude of force on each other and m is smaller, then A will be larger. And remember that the final speed is going to equal to the acceleration times the time over which they're pushing on one another. So everything else being equal, the lower mass results in a larger speed. So person A will be going faster. Newton's third law is really useful to us because up until now we've been only able to solve the very simplest of problems in which there's only one object. And we might say that we are pulling on that object or pushing on that object with a force, and then we can calculate things like what will the acceleration be produced on that object. Well, we can find it from calculating A is the force divided by the mass, and if this is a string that we're pulling, then the tension in this string will be the force that we're pulling on the object with. But we're only able to handle basically one object systems. What about complicated systems like a string of blocks, each connected by a string, and we're pulling on the farthest most right block here, and they each have different masses, M1, M2, M3. Well, each of these things is going to start accelerating together as a group. There's going to be some tension in this string that's pulling that mass, and there's going to be some tension in this string that's pulling actually this pair of masses. How do we know what these tensions are, and how do we know what these accelerations are of these different blocks? Newton's third law allows us to start making relationships between the various things and the various objects in the problem, because we'll know that the force from this object onto mass number 2 will equal the force from number 2 acting on number 1. A general strategy for solving Newton's law problems, it seems to work every time, is for a very complicated multi-body system to imagine each body as if it was there by itself. And we draw what's called a free body diagram. Free meaning ignore everything else in the picture and just draw a diagram which shows only the forces acting on this one particular object that you've chosen to isolate. Only show the forces on that one object. The next step is to establish a simple coordinate system, something that allows you to make calculations easy depending on whether the axes line up with all the forces that you're looking at. And you'll know that after you've drawn the forces. The third step is to write down a Newton's law type expression like the sum of the forces equals the mass divided by the acceleration, but you have to do that in all 3 dimensions of a problem. So the x direction, a y direction, and a z direction. You have to write sum of forces equals mass divided by the acceleration in that direction. And then, if there are a lot of bodies in the system, let's say there are n bodies in the system, you have to repeat this process 1 through 3 for each body in the system. So for body number 2, you have to write down a little diagram that shows you all the forces acting on body number 2. Again, think about a coordinate system for that one, and write down a Newton's second law type of expression for each of those that particular body. Now you're going to have n bodies in the system and 3n such equations from step number 3, and usually that means you'll have a lot of unknowns, but when you have the same number of equations as you have unknowns, you'll be able to solve for everything. So don't worry, don't panic about having too many equations. They should be all solvable as a system of a bunch of equations. And then, if you've done a lot of algebra to get all these calculations right, you're going to want to go check and see if you did it right. So I always find it convenient to go back and look at limiting cases just to check your work. Because even though the algebraic expressions might be complicated, there might be some extreme case which is easy enough to look at and say, oh yes, I've got it right.